So I'm going to talk about basically, something related to in-memory, but something in a slightly broader context than just the memory technology itself. I'm going to talk about how one should go about building next generation analytic platforms. And I'll show how you can do this effectively using Oracle database in memory and Oracle's Converged Database model. Let's see, here you go. Safe harbor, I'm supposed to show this for the lawyers. The basic thing that underlies any in-memory transformation is the need for modern enterprises to become real-time enterprises. And this is essential for an enterprise to survive in today's era. And what a real-time enterprise means is something that makes up actual data. It's data-driven, uses metrics based on real data. It basically continuously adapts to that data, so it's agile. This is required. It's not sufficient just to measure things. You have to also respond to your measurements. And then finally, the enterprise needs to be efficient. In addition to sort of reacting in real time, it also needs to adapt its business processes over time to continuously optimize productivity and profitability. So these three things really constitute what a real-time enterprise needs to be. And there are many examples of real-time enterprises in the real world. I'm not going to go through all of this in detail, but as you can guess, insurance companies need to do real-time pricing of policies and look at risks and in order to determine premiums. Retailers often use location-based metrics to send coupons, promotions, etc. Manufacturing processes and continuously optimize quality parameters. They observe and measure and then react and make sure that nothing defective leaves the assembly line. Financial services, they do risk and fraud analysis across multiple channels. The goal is to catch fraud before the fraud happens, not after the fact when it's too late. And of course, telecom constantly observes the network, makes sure that the network quality parameters are reasonable and to guarantee good quality of service. Right. So the thing that makes it difficult for enterprise to become real time is complexity. Now, for those of you who've ever been to India, this is a very common sight on many street corners. I'm sure Venkat, you can relate to this as well. I pity the electrician that works on this junction box. But this happens in enterprises too, where you have multiple systems, many technologies, many implementations, which hurts everything: security, administration, diagnosability, disrupts agility and efficiency. And this is a real example of real world complexity, and I call it die by DIY, where there is so much do-it-yourself technology here. It's very, very difficult to adapt, evolve, and make this architecture agile. There's multiple technologies, multiple data stores. We call this copy contagion, where the same data is present in multiple repositories. This hurts security, compromises consistency. Maintaining this, I don't know how anyone does a backup consistently of a system like this. And it's possible to get this to work, but it needs like a team of MIT PhDs and and the Stanford wizards to run this infrastructure. So this is sort of the equivalent of the Indian street corner street light junction box in a way. So I'm going to actually do something interesting today, different from the normal presentation. I'm going to design an application with you, because I thought that might be fun to do over a webinar. Hey, let's say if you were to architect a brand new application, how would we do it? And I had to pick a name that I wouldn't get sued for using, so I figured Magna Cart is safe enough. The people who framed the Magna Carta are no longer able to sue me for using their name, but I figured this is a good application paradigm to think about in the context of designing modern sort of web scale applications. So again, in today's sort of pandemic era, online deliveries are very important. And so this app is an app that includes multiple actors. There are customers that place orders, stores that process orders, a delivery service that delivers orders, and of course, there has to be an analyst or a team of analysts that checks the business overall. And the app logic must include transactions for placing orders and doing deliveries, also for rating deliveries and merchants and so on. And of course, analytics for both instant decision making and for continuous business optimization. So this is the high level goal for the app. Let's look at what this app might look like, right? So first of all, the primary actors that do work on the app are customer stores and delivery, service people, and delivery service itself, sorry. And customers browse items, create orders, the stores process orders, they deliver orders, they actually arrange delivery, they don't deliver themselves, and then they restock products. And the delivery service, basically, their job is to schedule delivery, pick up from the store, deliver to the customer. So, the first step is to define a simple set of OLTP tables, transactional tables that do this. So what do we have? We have customers, orders, items for each order, stores, the delivery, operations, then a list of products, the product catalog, and then each store needs an inventory of how much of each product it has. So this is the basic high-level transactional schema, fairly simple, just 7 tables. You also need relationships. So the way the relationships work is each customer has placed multiple orders. An order has multiple items from a single store. An item is attached to a delivery and a product. Some very large orders might get broken in multiple deliveries. So the item has a delivery, not the order. And a delivery contains multiple items and has a single store and a customer, recipient customer. And the store maintains an inventory of each product so that you can figure out how much of a particular TV brand each store has. That is basically the inventory. It's a many-to-many table, which is fairly common in relational schema designs. So each of these relationships correspond to an index. So we had tables first, and then now we defined indexes. The indexes correspond to relationships and defining keys. So each of these tables has an ID column that is a primary key. And then each of these relationships where a customer has multiple orders, there's also going to be an index on the customer ID field in the orders table, so that you can also look up all the matching customer IDs very quickly. So again, we have now basically the tables and the indexes, and things look pretty good to run transactions. So with this, we can now get an operational database up and running. You have one database with multiple tables. The database has OLTP indexes, and the principal actors all are fairly happy running transactions on this single database. So it's simple. It's single database, simple schema, simple architecture, fast transactions. And that's probably step 1 of Magna Cart, being production. However, we quickly find out that we need to do more than simply run transactions. There are things we have to do that are basically analytic in nature that enable these transactions to run. So before I can buy something as a customer, I want to find out what the top rated product is, which stores have it, what other things do I need when I buy this phone, for instance. And the store will have to also check to see, hey, what products are running out of stock, what are running low, which orders are the oldest pending or the highest value, so I can prioritize between my orders. And the delivery service obviously wants to optimize deliveries. It may want to make multiple deliveries on a single trip and prioritize stores which have the most pending deliveries. So again, just to get my basic business transactions running, I still need to run these analytic queries. And these are what we call real-time analytic queries. Without indexes, these queries run really slowly. As I mentioned in the earlier slides, I have indexes for the transactions, but I didn't define any indexes for these analytic queries. So I have to go back to my drawing board again, look at the database, the schema, and say, you know what, I actually need to index almost every single column in this schema because some analytic query might need it. For instance, I want to find the top rated, like phones. So I need an index on category to find out all the phone category products, and then an index on rating. And as you start adding real-time analytics, you find bit by bit, drip by drip, you end up indexing almost every column in the OLTP schema so that your queries run quickly against those tables. So now we still have a fairly simple architecture. It's still a single database, still a fairly simple schema. But now I've added analytic indexes which add overheads. The database size becomes bigger. They slow down transactions because every insert or delete has to maintain these indexes. The other bigger issue is that I have to be like a sort of a predictor of the future to know what index I need. It's very common to encounter databases that are heavily over-indexed just in anticipation of potential future queries, because you don't know what you might need in the future. So they require knowledge of the workload. So it's still simple, but you can see complexity is approaching. But then things get worse. The business analyst comes and says, hey, I need a totally different type of information. I want to optimize the business. So I need to know which products lead to the highest margins, which are the most productive stores in the Northwest region. If I start discounting flour during the pandemic, how much could our margins improve? Because I would increase my volume of sales of flour. So anyway, these questions they require a lot more data, sort of data intensive operations. They typically look at historical large volumes of data. And while you can probably get them to run on the operational database, most systems decide to offload them to a different database, basically to a data warehouse, which is where these analytic queries are better suited to run. Now, data warehouses have a totally different schema from the OLTP schema. As I mentioned in the OLTP schema, I had a set of 7 source transactional tables. But in the warehouse, all I really want to see is sales by customer, store, and product. Now, this is called a star schema. It's a very typical data warehouse design where I convert that OLTP style sort of schema design into a star, where there's a central fact table of every sale of each item, and then dimension tables describing that sale. So a dimension table for customer, products, and stores. Again, in a conventional database, all of these columns need to be indexed on the data warehouse so that you can run these analytic queries efficiently. What happens then is you've suddenly more than doubled complexity, because now there's a second database to which you have to extract, transform, and load the data because the data is in a different format. This database is a star schema. It is not the standard OLTP normalized schema. So the data has to be converted and the data has to be indexed also on the data warehouse. So now I've got another database with a different schema that needs expensive transformations and indexing. So things are, going downhill steadily, complexity-wise. Now it gets even worse because there are going to be other queries that people say, now, you know what, I am a store or I'm a delivery service. There are things I need to see on a regular basis. And we call these sort of dashboard reports. Most applications, most actors will have dashboards saying, what have I done for the year so far in my sales? What is my growth in sales? What are my top products? How many deliveries were made? Even customers might have dashboards showing, how many products they bought, what their total expenditure, their total, spending was, what products they might be likely to see an interest in next month. These dashboard queries basically can run very frequently. And because they run frequently and they're still pretty resource intensive, the way you run them more efficiently is to create pre-computed summary tables for good performance. So you don't end up recomputing these metrics over and over again. And it's because the warehouse serves this diversity of reporting needs from short and long term that you do need sometimes to cater to the short-term needs by creating these summaries. So I might want to create summaries like my quarterly sales, my monthly deliveries, my top products on the warehouse, and again refreshed internally from the star schema as materialized views. So this is a very typical design for a data warehouse, to have the source star schema tables as well as pre-computed summaries. Now, you can see Magna is getting more and more complicated. Now I have OLTP tables, indexes, analytic indexes on the left, and another database with a star schema and pre-computed summaries on the right. And the different actors have to look at different databases. So the first problem is that the warehouse itself adds a lot of complexity. The new system to manage requires ETL, usually lags, it's usually not up to date with the operational database. As transactions commit in the operational database, they don't reflect immediately in the warehouse. It takes time to get that information up there. The indexes all add overheads. Again, as I said, they require advanced workload knowledge, they slow transactions down, they increase the database size. And pre-computed summaries or materialized views add more complexity. They lag the source tables again, and they add additional resource load and increase the database size. So between these two databases and all these indexes and summary tables, suddenly there's a lot more moving parts and a lot more operational complexity. Now, what we really want is something very simple. We don't want any of this. What we want is really one converged or unified database where I can run everything. I shouldn't need a data warehouse unless I'm trying to bring in data from multiple sources, and I'm not at that point yet in the Magna application evolution. I don't want to predefine indexes because I don't know what I might need in the future. And I want to run everything on one database. The question is, well, is this possible? Well, I'll let you guess the answer, but the answer, obviously, I wouldn't be asking it otherwise. The answer is yes, it is possible. And it's possible, and I explain why. The first technology I'm going to introduce is Oracle's database in-memory technology. In-memory is a technology that simplifies analytic application design significantly. The basic premise is there are two competing formats for your database data. There's row formats, which is fast for OLTP, but slow for analytics. There is column format that is fast for analytics, but really slow for OLTP. And then the best performance is achieved if you can combine the benefits of both formats into a single dual format, so that no matter what the operation, it gets the best of both worlds for any style of operation, whether it's aggregation or whether it's a lookup by primary key. So the way database in memory is architected, it's a dual format architecture where both these formats are simultaneously active and consistent at the same time. The optimizer automatically chooses the row format for transactions, producing very high transaction throughput. And analytics automatically are directed to the in-memory column format, which is ideal basically for analytic operations using a variety of techniques that I'll talk about next. But the basic, the basic sort of the metric here of interest is that the column format can service billions of rows per second scan speeds on in-memory columnar data. So very, very fast format for analytics. It's not great for OLTP, but it's very good for analytics. And the in-memory column format is new. It's a new in-memory format added to Oracle database. The format can be maintained purely in memory, so transactions are much faster than having to maintain indexes. There is no change needed to disk formats. It's available in any platform that runs Oracle database. Most importantly, any Oracle database feature, like availability, security, etc., they all work transparently when this format is enabled. It does not require the whole database to be in memory. Unlike many in-memory databases where the entire database has to be loaded into DRAM, the database in-memory feature lets you subset the database by any granule you like. You can bring in selected tables, selected partitions of tables into memory, depending on what you need real-time reports for. In the Magna example, you don't need the whole database in memory. You need basically the stuff that needs to be in memory to facilitate real-time reporting. So you can actually subset intelligently based on your workload's needs. One of the key underlying principles of in-memory processing is SIMD vector processing. First of all, the column format itself has a benefit because you only have to look at the columns you need to look at for a certain query. For instance, if I'm looking for sales in California, I just need to look at the sales in the state column. I don't need to look at every single column in the row. Then, in addition to that, when I do in-memory processing, I can process multiple values in one instruction. So I can compare, for instance, all the multiple values of state with California in one cycle, leading to a massive acceleration in performance. This is only possible when you have contiguous storage of column values. And this is a key reason why in-memory columnar processing can deliver billions of rows per second scan speeds. And no matter how fast your row format is, how clever your programmers are, a row format database can never scan at more than a few million rows per second, which is why you need indexes on row formats. With the column format is so fast, you do not need indexes. It's like 100 times faster, on an average, than scanning the row format. There's lots of technology underlying in memory, which I won't go into any detail on here, but there's tons of information available online. The column format lets you, of course, access what you need. The SIMD vector processing technologies let you process multiple values in a single instruction. In-memory storage indexes let you prune out unnecessary data. Even within a column, you can eliminate data through these in-memory indexes that tell you if the value you're looking for is actually within the range of this column fragment. So I can, if I'm looking for the value of say 9, I know I can skip the first 2 units here and go to the third one and scan only that. And then of course, in-memory columnar formats are very, very compressible. They're a great method for they're a great vehicle for data compression because all the data is contiguous. So it's easily compressible, and the compression gets you not only more capacity, but it also improves performance because you take fewer CPU cache misses to access data. In terms of the in-memory processing, it, like in-memory is designed to accelerate every single aspect of analytic processing. I mentioned scans. They run fast with essentially, columnar storage and with vector processing. Joins also become faster because I can essentially convert joins into a series of scans. If I'm looking for only sales of phones, for instance, I could first figure out which products are phones in the product table, and then build basically a large in list of phones, and then scan the sales table looking for sales that match those product IDs. So essentially, instead of doing an expensive join, I've created like a super fast series of scans to basically process my join. And then in-memory reporting uses the same techniques to convert complex aggregations into essentially fast filtered scans. And this actually, I would like to say a little bit more about because this is a very interesting optimization. So imagine a query where I'm looking for swimwear in California stores. It says footwear here, ignore that, please. That's a slight typo. So the first thing is I scan the products table looking for swimwear products. And then I scan the stores table looking for stores in California. Then basically what I do is I build an in-memory spreadsheet that has a cell for each swimwear and California store combination. So every store in California and every possible swimwear apparel item has an entry in this cell. Then I simply scan the sales table, and for any sale where the sale corresponds to a California store and a swimwear item, I basically increment the corresponding cell in the outline by the amount of that sale. And it's trivial at this point. Basically, instead of doing a complex join with group by, I've basically converted this operation. I've deconstructed it down to a series of fast filtered scans, which is what gives me my 10x faster reporting. It's a very cool optimization. The technical name is vector group by, but think of it as almost instant reporting without the need for a pre-computed summary. Again, the other benefit of in-memory is because scans are so fast and indexes, as we know, have overheads. They make the database bigger. They need to be anticipated in advance. They slow down transactions. Because scans are so fast with the in-memory column store, I can replace those indexes with the in-memory column store. Now I've reduced my database size. I get fast analytics on any column. So ad hoc reports run really fast. And because the in-memory column store is not persistent, updates are super fast. So, Magna benefits from having the in-memory column store as well, instead of the analytic indexes. Now, another cool capability, because one question somebody might ask legitimately is, okay, well, what about very large tables or historical tables that I don't want to bring into memory? And there is a great solution for that with database in memory too. It's because we have in-memory technology available in both the storage tier and the compute tier. We can offload in-memory processing to the storage tier. In the Exadata database machine, we run both database software and storage software. We build that software on both tiers. And what we have done is extended the in-memory format into the storage tier in what we call the smart columnar flash cache. This gets you massive expansion of the total columnar capacity, up to 500 terabytes on a full rack X8 Exadata. So if you don't want to bring your data into memory for certain queries, maybe they don't fit in DRAM, maybe they're old and they don't really are not accessed frequently for real-time reporting, you can use the in-memory format on flash to get massive performance benefits for your queries that you want to offload. And this basically replaces the need to offload to a separate data warehouse. This offload is transparent to the application. It just runs automatically. And there is no need to create a new schema or do any new DDLs to define new sets of tables. The queries run transparently. Just, if you're running against in-memory tables, it'll run on the compute. If you run against in-flash tables, it'll run automatically on the flash tier. So you still get the benefits of in-memory columnar processing, but with much higher capacity. In-memory has been around for a while now. We, I think, launched it first in Oracle release 12.1. We've steadily, enhanced it in subsequent releases. In the most recent release, we have a lot more self-managing memory. We've expanded the scope of in-memory to handle other workload types like, spatial queries and text analytics, allowing hybrid scans across different data formats, and so on. So this is like a very active technology, very, it's been developed actively and aggressively, and we keep enhancing it in each release. I'm not going to say much more about this, but there's tons of information about in-memory, and I have a few slides at the end where you can, if you're interested, you can take a look or take a screenshot, and you can go look up the websites and get more details on each technology here. But the big point I have to say about in-memory is transformational. Air travel transformed society. It didn't just make travel faster. It was a lot more than that. It changed almost every aspect of our life. I think the fastest Atlantic crossings took about, 5 days in the 1950s. Used to take a couple of weeks in the 19th century, but in the towards in the 20th century, ships got faster. But I still think the fastest crossings were around 5 days or so. And often people would create wills before they took a long ocean voyage. With air travel, it changed everything, changed business, trade, politics, education. There was no seasickness anymore, just jet lag. And hopefully we'll all travel one day again to enjoy jet lag. Right now, actually, to me, jet lag is a privilege. It's not actually a negative thing because it means I'm traveling somewhere. But yes, air travel transformed basically society. The same thing with in-memory. It doesn't just improve performance. The fact that you can get instant results means you can make decisions more quickly. The fact that there are no new systems required give you total lower cost. And your overall architecture becomes much simpler, much more agile. So you basically have a much leaner, much simpler overall enterprise analytics deployment with in-memory. Actually, it's not just database memory. I think this is broader than just the Oracle technology. That's one thing I love about this conference, that we all speak the same language, that in-memory is very, very important. And the key thing for all of us to know as a community, it's not simply just a single discrete technology that makes things faster. It really lets you do things in a fundamentally different way. And it's pretty clear to me that the next 5 or 10 years, non-in-memory will become like essentially Windows 98 or rotary phones or something. So in-memory is going to become the future for all enterprise architecture. So again, if you look at the Magna card example, in-memory brings us the simplicity we were looking for. Now all these actors can now run on that same database, just with OLTP tables and with OLTP indexes. And the reason is the in-memory column store replaced the need to create these analytic indexes, step one. In-memory on flash replaced the need to create a disjoint data warehouse. And the in-memory reporting technology I described, the thing that creates reports in real time from a series of scans, that's all that basically makes it, in memory it makes it unnecessary to create pre-computed summaries. You can now run these reports in real time without needing to predefine expensive to maintain pre-computed summary tables. So all your quarterly reports, your sales to date, top products, you can just run those queries at will using the in-memory reporting technology solution. So you get really fast transactions and analytics against all your data without having to have prior knowledge of the workload. And it runs all on a single database, which you can then, of course, scale out to any size you want. But the point is, you don't need to manage multiple systems to run this workload anymore. In-memory is a very widely used technology in Oracle, in the Oracle customer base. Lots of customers with a variety of different applications. One of my personal favorites is Lufthansa, because I love traveling and I look forward to traveling again. And I think back wistfully of all the travels I've done until the beginning of this year. So Lufthansa uses in-memory for a very interesting use case. They actually use it to do analysis of aircraft when an aircraft is basically put in the bay for maintenance. And they call this process a D-check, which runs every few years, 5 or 6 years. They take the entire aircraft apart from nose to tail. And each part, they have to verify and decide if it needs refurbishment or not. And in the past, this is a massive logistical process, obviously, but the reporting queries in the past that would actually run to see which parts needed refurbishment took a long time to run. And you can imagine the amount of data these queries have to process is enormous. A 777 probably has like 6 million parts in it. And so there's a lot of ingestion of data required and then analytics on those ingested, ingested data items. With in-memory, they not only improved their ingest performance, they got the queries to run massively faster, and they reduced the database size. So I feel very happy and proud that Lufthansa uses in-memory to keep aircraft safe. Lufthansa is very, very good at aircraft maintenance. So many airlines actually outsource maintenance to them. So if you travel to Frankfurt, you'll see one of the world's largest aircraft hangars in Frankfurt Airport that contains aircraft from many airlines, which are undergoing this D-check by the Lufthansa technician. So very, very cool application, I think. We have other many interesting use cases of mixed workloads as well. Bosch, again in Germany, uses in-memory to speed up an OLTP workload. In fact, their requirement was not to speed up reporting. Their real issue was that their reporting queries their DML and batch jobs were slow because of all the indexes they maintained. So Bosch actually was able to drop all their custom indexes on a very complex OLTP schema called SAP CRM. And they got back their batch performance, and their queries also ran faster as a result of it. So again, in-memory is an action in multiple use cases to speed up both analytics as well as OLTP. The other thing that gets you simplicity apart from in-memory is convergence. Now, it's going to happen to Magna. Magna is just, it's taken its first baby steps in application. We got it running on one database, but it's going to need more algorithms. We're going to have to bring in unstructured data support, graph support, machine learning to do predictive analytics to see which products need to be stocked next year, maybe, potentially. So lots of cool algorithms will be needed. Now, one approach is to do what I show on the picture here. I could do this using a variety of databases that do each of these functions independently, and then communicate between them to handle this, this evolving workloads needs. This, again, is going to take you down the path of complexity. A much better approach is to use a converged database. Oracle database actually has a really good converged database model with best-in-class support for all workloads against all types of data. It has really good relational support, obviously, but also has class-leading JSON graphs, spatial files, and a very large machine learning portfolio. So you can actually run your, you can run your training and inference in the database without having to extract the data to an external framework. And you get the benefits of simplicity, lower cost, and reliability. You get to use the same security policies across all the data. You eliminate copy contagion, having multiple copies in different stores, and eliminate this complexity of integration using events to keep these different databases in sync. So much, much simpler and much lower cost approach to running a complex workload. Because it's a matter of time. And nowadays, no application ends up being purely a simple relational application. Applications have to adopt multiple data models and workload types. So this is, the need is real. The question is which path we want to go down. And I think it's pretty obvious that the path sort of listed below, the Converged Database Path, is a path towards simplicity, whereas the path above is a path towards this, babel of complexity. And on top of that, if you wanted to get a simple converged database up and running, the easiest way to do that is to spin up Oracle's autonomous database. Oracle Autonomous Database basically takes away the guesswork and trial and error and manual management of databases. What really turns people off databases, especially developers, is, hey, I don't want to increase my complexities by having to manage this complex product, and databases are complicated. But Autonomous Database hides that complexity and sophistication by basically being self-driving, self-securing, and self-repairing. First of all, the Autonomous Database is self-driving. It scales out, based on the workload's needs. It runs on the best possible database platform, which is Exadata, but it hides all of that sophistication from the end user. And if you have Oracle databases anywhere on your enterprise, it's fully compatible. So there's no problem bringing data in from the existing Oracle database into Autonomous Database. It is self-securing, so you never get security breaches again. It automatically applies patches. It's fully encrypted. It hides sensitive data both from your own admins and from Oracle, the cloud administrator as well. It's self-repairing. It actually, repairs automatically if there's a failure. Guarantees very high uptime, and like I said, it elastically scales compute as needed. So this is Autonomous Database. Now, it is very, very easy to get started. And I've actually been doing this myself to just get a feel for how simple it is. So you can actually now go up to Oracle Cloud and sign up for the Cloud free tier. And you can there create yourself a database that's autonomous, either for transaction processing or for analytics, either way. And once you've done this, you can then go to your database you just created. This is a database I created just a few minutes ago, actually today. And then you can interact with it using a variety of different, actually, web-based tools. So before you write any actual code, you can get pretty far using SQL Developer Web and Oracle Application Express. I don't have screenshots for those in this presentation, but they're pretty self-explanatory. In many cases, you don't need to go beyond this low-code development style. Many applications are perfectly happy being developed in SQL Developer or Oracle Apex. And Apex is a simple sort of graphical screen-by-screen application builder that you can actually write very sophisticated applications for. So in many cases, you don't need more than that. Now, of course, you can go far, far deeper. You can certainly do programmatic development as well, and that's all listed under the ATP portal as to how to move forward in your development journey. So very cool stuff, very simple, very easy to get started with developing applications for Autonomous Database. Okay, so with that, I think I'm going to wrap up. But I wanted to say that basically, I've actually seen this with customers and friends and colleagues who manage infrastructure, and I feel like there's 5 stages of responding to or handling complexity. Okay, so the first thing is, of course, you have that. So the first stage, I think, is a stage of denial, where you look at that and say, you know what, that thing actually is very simple because I know where every single connection goes. So it's actually extremely easy, no problem. It just looks complicated, but it's actually very, very simple. So this is the first symptom. It's called denial because it's not simple. The second thing that you sort of encounter is pain. And the pain is when it actually gets, when it breaks, it's broken. That's painful because now the thing I said that was actually simple is not simple, it's broken. After your pain is addressed, then the next stage is anxiety because it's not broken now, but it's going to break again at some point. So now you're worried about the next breakage. You're no longer at peace anymore. Your denial is gone. It's complicated, it's going to break again. Then you get into depression because there's a cycle of constant breakage and fixing and breakage and fixing. And you say, you know what, this thing is always broken. My life is a disaster and I have to manage this the rest of my life. So that's depression. it's very negative. It's a, your negativity sort of takes hold at that point. And finally, to deal with that, then of course, I'm not saying I've seen this happen to people, but it could happen that you get into substance abuse. You say, you know what, it's just this one time, I won't do it again. It's just this one escalation. So once this escalation is done, I'll go back to being completely, I'll behave well, but it's just this once. I promise, only once, never again. So that's the 5 stages of complexity: denial, pain, anxiety, depression, and substance abuse. And my advice is just say no. I will not go down this path. I will avoid complexity. And there is a quote that somebody, from someone, I've forgotten whom, but the quote is meaningful. That simplicity is basically the result of resolving complexity. Complexity is the inevitable outcome is you must resolve it and create simplicity. By the way, I mean, the quick thing to point out in computer science and technology, historically over the years, the things that have been successful are basically things that are inherently simple. So just look at, for instance, JSON versus XML. JSON became far more successful as a data model because it's inherently simple. You can build complexity on top of JSON in your format, but it's inherently simple, whereas XML is inherently not simple. And the same thing with other concepts, like file systems became popular because a file system is inherently simple. It's open, close, read, write, very, very simple. And that's why file system became very popular as data, as data management solutions. There's lots of examples like this. REST became popular. It basically much more popular than, Java RMI or SOAP, excuse me, because REST is inherently simple. It's very, very simple, stateless, very easy to build application on top of. And the same thing, with Converged Database, you basically get inherent simplicity that lets you build complexity on top, but the solution itself is not inherently complex. Anyway, I'll get off my complexity soapbox and try to wrap up now. If you're interested, it's very easy to start with database and memory. You can do this easily if you wanted to download your own database. You can get a free Oracle Express Edition download. And I've created these short URLs because the URLs would be too long to fit on this slide. But if you need to take a screenshot, please feel free. Oracle 18c-XC is available, includes in memory up to 2 GB, and you can actually get a decent amount of work done with it to kick the tires with. If you want to try something on the cloud, Oracle's Exadata Express service includes the ability to create a column store of up to 5 GB in size. So that's an easy way to play with in memory on the cloud. And if you have an Oracle Enterprise database, and I believe it has to be at a release beyond 19.8 or beyond, we have something called the free in-memory base level that gives you up to 16 GB of free in-memory column store per database instance. So if you have an Oracle deployment, you can easily create this 16 GB in-memory column store. In-memory is normally a licensed option on Enterprise Edition, but the base level is free as long as you have Oracle Enterprise Edition. So these are 3 ways that you can easily get started with database and memory. And if you want more information, we have an in-memory blog that has the latest updates at any time of what's going on in the technology. The technology is overviewed on the Oracle main website under database. And I would definitely encourage you to look at the Oracle Autonomous free tier. As I mentioned, it's very easy to get started with an Oracle database. You can go, create your own OCI cloud account and free account, and then create a database. If you get $300 in free cloud credits when you sign up, but if you don't want to pay, you can stay with a forever free account after that. But I think when your trial ends, you have the option to upgrade to a paid account, but you don't have to upgrade. You can keep it forever free. But you do have the ability to burn $300 worth of free cloud credits while you're in this trial period. So that, I think, is all I had. So Venkat, I think I was on time.
Perfect. That was great. Thanks.